Hello everyone, my name is Amanpreet and I'm here today with my group members Athinder and Mulu to present our project Cross-Site Scripting Detection using Machine Learning. Here is the agenda for today's presentation. First, we have an abstract, followed by introduction, literature review, which is all about the study and research done about cross-site scripting, the research methodology, implementation, and then we also have a live demonstration of detecting XSS attacks and sending a pop-up notification to the client. After the demo, we will share a few of the limitations of our solution, followed by a conclusion and future work. So, cross-site scripting is one of the topmost occurring type of attacks in web applications. One reason for these alarming rising attacks is the common vulnerabilities found in web applications, including poorly written code or lack of data sanitization in web applications. This leads to insufficient input validation from both the client and server, and it opens up the possibility for an attacker to inject malicious script to be executed in the user's browser, which further leads to stealing sensitive data. Our research shows that there are various methods used to analyze XSS vulnerability. Our findings show there were missing HTML and JavaScript features extracted in identifying XSS attacks. Therefore, our project focuses on filling the research gap by combining URL-based HTML and JavaScript features along with DOM objects to improve the detection of XSS vulnerabilities. The solution has implemented a Python program that is capable of intercepting HTTP traffic, and the program is deployed on a server for analyzing the intercepted HTTP traffic. Here's a quick introduction. Cross-site scripting is a vulnerability in a web application that allows attacker to inject malicious scripts that affect other users on the website. Numerous websites have been attacked through this vulnerability, which has damaged their reputation and value. The Open Web Application Security Project claims XSS attacks are ranked 7th on its top 10 web application security risks. Additionally, Common Weakness Enumeration ranks this attack at number 1 for 2020. Based on the recent studies, more than 60% of web applications are vulnerable to XSS attacks, which eventually account for 30% of all web application attacks. There are three types of XSS attacks: persistent, non-persistent, and DOM-based. Persistent attacks inject malicious scripts that are permanently stored on server resources. For instance, websites allowing clients to post comments are prone to persistent XSS attacks, as the attacker can include a script in their post. If another user visits the same web page, the script is automatically executed without any victim interaction. Non-persistent attacks inject malicious code into the client's browser without being stored on the server. Once the victim clicks on the maliciously crafted URL, the script is executed on the victim's browser. This technique is prevalent in phishing, as the attacker will email a link containing the malicious script. Lastly, the DOM-based attacks inject malicious scripts into the URL that will modify the DOM tree. When a user clicks on the attacker's maliciously crafted URL, the page's layout will include the script's modifications such as tables, links, text. This technique is harder to detect as it does not load into the source code as part of the website on the web server. Therefore, the objective of our project is to build a Python program to detect XSS vulnerabilities by extracting URL-based HTML and JavaScript features to train our machine learning model. The program is deployed on a network monitoring server. It's a device that intercepts the HTTP traffic and extracts features from the captured URLs. The program classifies web application as malicious or benign based on a trained machine learning classifier and alerts the client with a pop-up notification for detected XSS vulnerabilities. To achieve our objective, we came across some previous work done to analyze XSS vulnerabilities. We have reviewed different XSS detection techniques that use static analysis, dynamic analysis, and machine learning in detecting XSS. Static analysis. Static analysis examines the program's code to predict its behavior during runtime. The client-side approach reviews the policies set in place on the client's browser, whereas the server-side examines the flow of data in the source code of web application. The static analysis approach was limited to examining the source code of the application, which could not confirm the vulnerabilities until the application was executed due to missing HTTP response that confirms the existence of a vulnerability. In the dynamic analysis, the approach uses black box testing techniques, such as vulnerability scanners, to assess web applications. The assessments are conducted while the server is running to identify vulnerabilities in real time. There are three different methods to detect XSS vulnerability in dynamic analysis. First is the client side, second the server side, and the hybrid. The client-side approach focuses on examining the browser-embedded functions to detect XSS attacks. In contrast, the server-side approach concentrates on analyzing the server hosting the application for vulnerabilities. And the hybrid approach focuses on using proxy-based or browser-embedded solution on both the client and the server side. Dynamic analysis could not detect unknown attack vector that bypasses the XSS filters. And the next is our machine learning. The machine learning is a key concept in our research that provides a better detection approach for XSS vulnerabilities. We have came across various algorithms that are used to detect XSS vulnerabilities. Most of the solutions focused on extracting either URL, HTML, or JavaScript features to train their algorithms in identifying XSS vulnerabilities. Here, this table shows some of the reported performances of some of the machine learning solutions we came across in a literature review, along with the models used in each solution. In the first, we have the literature review of Capstone 2019, where they extracted words in an HTML request to identify suspicious patterns, and they used the decision tree as a classifier. They could not get more than 86% of accuracy due to a very small dataset used to train their model. And the second one, they have used the decision tree and naive Bayes algorithm in the experiments. However, it is only the decision tree that yields higher performance. They extracted words in the JavaScript code to identify suspicious patterns using the tool Word2Vec. These words are plotted on a three-dimensional chart based on the frequency of appearance to detect suspicious patterns. Even though their model provides high accuracy, it also generates high false negative alerts, which is shown in the lower rate 93.7% of sensitivity or recall. In the third one, the authors conducted an experiment based on three different types of features, such as URL, web page, and social networking services. The experiment yields a consistent score in accuracy, precision, recall, and F1 score, which shows balanced false negatives and false positives. However, the experiment was focused on social networking services only. In the last one, they have combined naive Bayes and sport vector machine classifiers to detect XSS vulnerabilities. They focus on features extracted from web document content and URL. Their results demonstrates that the proposed features lead to highly accurate classification of malicious pages in both models they have used. So the lessons that we have learned from these experiments that the experiments conducted using decision tree classifier produced satisfactory results. So we decided to work with decision tree in our experiments to get improved performance in detecting XSS vulnerabilities. Secondly, we also found that there were only limited experiments done with the SVM classifier. So we decided to test the SVM as a second algorithm for our project. Additionally, we learned that combining different types of features produces better results. Therefore, we have decided to combine all major types of features that are URL-based HTML, JavaScript, and DOM objects for our experiment. Next, Atender will continue with the project diagram flow and the research methodology.
So the diagram here shows the complete overview of our project. The development phase is the focus of our research methodology, which includes the data collection, data pre-processing, training and testing phases for our model selection. Then in the implementation phase, it shows the process of capturing traffic, feature extraction from the captured traffic, and feeding it to the model for classification. So as we highlighted in the project diagram, the research methodology consists of data collection, data pre-processing, and model selection. So for a data collection, the data set we use to train our classifier is built using a list of payloads obtained from trusted sources. This data set contains a list of 20,818 payloads, including URLs and plain text of malicious and benign contents. The malicious payloads cover 35% of the whole dataset, whereas the remaining 65% are benign. For, for data pre-processing, to build the dataset, we have extracted attributes that consist of 62 features that are commonly found in XSS vulnerabilities from the payloads. Our feature extractor function looks for matches in the extracted payloads, and for every match found, it labels it as 1 and 0 for every non-match. In addition, it counts alphabets, digits, and characters in a URL and assigns them to their corresponding attributes as a normalized value. So missing data is also taken care of, and the data set is split into 70% training data set for the training phase and 30% for evaluation. So as we mentioned in the literature review part, based on our research, we shortlisted decision tree and support vector machine for our experiment. So we conducted various experiments to compare the two classifiers to get the best fit for our solution. The comparisons are based on our observation in accuracy rate, some selected evaluation metrics, and five-fold cross-validation. So first, we evaluated the two models' performance in terms of accuracy in classifying the evaluation dataset. As we mentioned earlier, the dataset is split into training and testing dataset. So the two classifiers are concurrently trained using the training dataset and evaluated using the testing dataset. We investigated the results of their accuracy rates as a starting point for our comparison. Decision tree classifier gave an accuracy rate of 98.8%, whereas SVM gave 99.1% of accuracy rate. So this result shows that both models performed well, where SVM predicts with a slightly higher accuracy. To further our comparison, we generated confusion metrics for both models that are chosen for selection. As we can see in the diagram, there is a low false positive in both models. However, decision tree resulted in higher false negative, which is 45 compared to 29 in SVM. This can be used to determine the various metrics that are listed in the table below. In all aspects, SVM slightly overperformed TT. Next, to ensure that the score of our model does not depend on the way we selected our training and testing subsets, we implemented k-fold cross-validation as the final comparison between the two models. The value of k is set to 5. Based on the 5-fold cross-validation we have used accuracy, precision, recall, and F1 score as recorded for both models in each iteration, and the mean is calculated for each matrix. The result shows that SVM scored high accuracy rate of 99%, whereas the mean for decision tree is only 97.8%. Not only in the mean, but SVM slightly overperformed decision tree in most of the tests in each fold and the metrics used. This result supports our previous observation and concludes our experiment for model selection. SVM is proven to be the model to implement as a classifier for our solution. Now Molu will continue the implementation and live demo.
Thank you. Implementation. Our project design consists of the clients and a proxy server through which the client is connected to the internet and the traffic is monitored on the proxy server. When the client visits websites, the proxy server captures the HTTP traffic and sends them to the Python program to be analyzed for XSS vulnerability. The Python program is designed to extract features, including HTML tags, HTML properties, event handlers, DOM objects, and so on from the URL that's captured. Here we have string parse and regex for feature extraction and Scapy for capturing the traffic. The feature extractor looks for match of the desired features in the extracted URL, and for every match, it labels them as 1, and for non-match, 0, and stores them in a list of attributes. In addition, it's normalize some alphabets, digits, and characters found in a single URL. Once we have our extracted data in the form of zeros and ones, the attributes are fed to our selected classifier for analysis. If cross-site scripting is detected, an alert message is sent from the server to the clients as a pop-up message. Now I will demonstrate what we have implemented. Okay. Here we have our proxy server and clients. The client is connected to internet through the proxy server. And here we have the scripts written in Python. The first one is the builds a data set from the payloads we have. We have also the classifiers. This one was for our experiment for the methodology to select the right model. Here we have the implemented classifier, and here is our program that captures the traffic, sends to the classifier for classification. Now first it sends it for extraction and then for classification. So I'm going to run the XSS detector. So it's running now, and the client has to be connected with the proxy server to receive the pop-up notifications whenever the client visits a vulnerable website. So for this purpose, we have a socket connection here. It's also running. We can check it with okay, it's running. For testing purpose, we went for cross-site scripting vulnerable websites. There is an archive. These websites, some of them are fixed, which are marked as green, and the red are not fixed. But some of them are not available too, since they are stored for archive from long time. This is from 2015. I'll let the client visit some of the still vulnerable websites. Here is the URL. That's by the time it was there, the website was vulnerable. If I try to visit this website, the proxy server should send a pop-up notification if cross-site scripting vulnerability is detected. Excellent. It's not going through, I think.
Well, I can try it on my machine.
It's not going through. The request is not going through. Let me see. Yeah, this one is going through, and here is the pop-up notification. And also the proxy server shows whenever it sends a warning message, it shows a pop-up that a warning is sent to the client. Yeah, it's showing up for the first one now. Yeah, now Paul will continue on the demo using DBWA by performing some cross-site scripting attacks.
Can you guys see my screen?
Yes.
Okay, thank you. So we have DBWA set up in our separate machine. I'm just going to show the IP address of this machine. So here's the IP address 192.168.60.13. So I'm going to run these scripts in my proxy server first. Okay, so my program is started on proxy. So I'm going to run the program on the client side. Let's just check it. It's running. Yes, it is. So from my client browser, I'm going to visit the DBWA. For the testing purpose, I'm going to set the security to low. Then I'm going to test some XSS attacks on these tabs here. First, I'm using a simple script tag. Check in our proxy server. There is a delay sometimes when you send the request. Okay, there we go. So it shows on the server side that it's sending the it sent the warning sent to the client, and then on the client side we have the pop-up message here. Okay, so let's try another attack. So this time I'm gonna add the script to the URL. So this time the script, so it has a script tag and a DOM object document.location. So if I go ahead with this. Okay, so another warning alert. Let's try one more. So again, script tab with another DOM object that's document.key. Okay. And then again, an alert is seen on the client machine that access is detected on this URL. Okay, so that's all for the demo. Now Molu will continue with the rest of the presentation. Thank you.
Limitations. Our solution is limited to client-side detection, and also sometimes notifications are noisy, and the program sends multiple notifications for a single detected incident. Conclusion and future works. First, we have discussed the problem, the cross-site scripting vulnerability and its impact on web applications. What's previously done to understand works done to resolve the problem. We have investigated some previous works done. After reviewing various solutions through our literature review, we have developed our solution to the problem. Our solution uses machine learning to detect cross-site scripting vulnerabilities using support vector machine or classifier, SVC, as our classification model, which was able to detect cross-site scripting with accuracy rate of 99% based on the dataset we have provided. Our solution is a client-side detection, and it can be expanded to server-side detection. In addition, the solution is limited to detecting vulnerabilities from non-obfuscated URLs, so some more can be done to detect cross-site scripting vulnerabilities from obfuscated URLs. This concludes our presentation. And thank you for attending. Now we can take your questions or feedbacks.
Thank you for presentation. Please ask questions.
Okay. What are the challenges of having to implement HTTPS intercept? It's implemented on HTTP. It's capable of capturing HTTP traffic only. It doesn't have a capability to capture HTTPS. I'm trying to answer Lloyd's question. What are the challenges of having to implement HTTPS interception? Yeah, since we had difficulty decrypting the URLs because they are encrypted, we had difficulties capturing HTTPS, so it's limited to capture HTTP traffic only.
I'll take the next question. Gaston asks, are the trained model persistent? If so, how? Or are they trained every time you run the script? So what we have done for our training and testing data set, we have collected the payloads where 35 of them were malicious and 65 of them were benign. And we have collected a data set of about 20,818 payloads. So no, they're not being trained every time. We have already included them, feeded it to the machine learning, and we use the k-fold validation method to test our program. I hope that answered your question.
To add to Gaston's question, are the trained model persisted? If so, how? Or are they trained every time you run the script? They are trained every time we run the script. There is no much difference they produce. Most of the time, it's 99% accuracy, and we ensure that they can be like consistent through our 5K cross validation too, 5-fold cross validation.
Next, Arnab asked, what was the most
I can
challenging?
take Arnav's question. I'm sorry.
Okay.
So we can go in now. Okay. So Arnav's question is what was the most challenging aspect of your project? So there was couple I'd like to mention about the traffic. So capturing the traffic and filtering the URL, the exact information that we wanted. That was the I would say the challenging part. It did take us a long time to properly capture the traffic and then get the exact URL that we wanted. So yeah. Molu, do you want to take the other question?
Yeah,
or-
I'll take Emma's question.
Yeah.
A great presentation. Were there other data sets looked at that could have been used where there is a lower percentage of benign payloads? Our data set is big. It's 20,000, and if we use 35,000 benign, it's still a good amount of benign. No, 65 benign and 35 malicious. So even though the number they are not in the same proportion, still they are like good amount, and yeah, and it hasn't been an issue.
Okay, I'll take the next question. Has your team considered also creating logs within the proxy server to record the URLs of the vulnerable website? It could be beneficial to also prevent further access to these sites and just overall blacklist the sites. Yes, I agree with your point that it could be beneficial to to record all the vulnerable URLs. It is definitely on our to-do list. For now, we do not have a way to log every vulnerable website in our proxy server.
Okay. I'll take the next question. Jane asks, why do you choose 7:3 as a ratio for training and testing? So well, there's not a specific specific reason. We just thought that it will be good to train the data set with the with as much data we can get. Like it will for training, it will give us better result if we use the most of the part. So for testing, we use the remaining part, but for the URL that we are detecting for every like single URL, so it takes the whole data set to give us the result for single URL. So there is no specific reason. We just decided on this number. Thought it will be good for the purpose that we are doing the testing for. I hope that answers your question.
Molly, you want to take the next one?
Yeah, Ernika, is the solution that you provide can be implemented in real world? If yes, how it can implement? Because it needs some more work to really implement it. But it has like, if we could cover the future works, the shortcomings on it could be implemented. The next
Aman,
question
you're
by
next.
Alex.
I'll take the next one.
Okay. Okay. Were there any web pages in practical that you were surprised were susceptible to an XSS attack? Yeah, there was some websites that are listed on XSSD that are that looks like banking websites or some legitimate like other well-known websites, and that's really surprising that they are susceptible for cross-site scripting attacks.
The last question is there any way to stop pop-ups of the XSS detected keeps on appearing? It seems very annoying for a user to have to keep dismissing them. Yes, I agree. This is our one of the limitation for our project, that our notification a little bit noisy, and there's also a little delay to it. So this is something we are working on improving.
Yeah, I guess that was all the questions for now. Yeah, thank you so much for watching the presentation. Yeah, thank you.
Thank you.
Thank you for answers, and thank you for all questions.
Thank you.
I thank you, presenters.
Thank you.
The next presenters, please publish the URL for the teams that we need to join. Thank you. And let's try to join. Let's go to the next session.